So we would like to listen from Dr. Brahmendra Kumar, Senior System Engineer. If for his introduction, I would now welcome Dr. Anil Kumar, the teacher of Brahmendra Kumar, because we are very much proud to introduce him from the representing Institute of Science and Technology of JNTUK Kakinada. Dr. Anil Kumar, can you introduce Dr. Brahmendra Kumar?
Okay, Brahmendra is ready? Okay, fine.
Yeah, please, Anil.
I'm glad to invite our JNTUK alumni, Dr. G.V. Brahmendra Kumar, who is working as a senior system engineer at Nexteer Automotive, Bangalore, India, from 2022 onwards. His skill set comprises of RIL testing and verification, control strategy development, Opal RT systems, DSpace, Kanoi, DNG, DOS, analog discovery, MATLAB Simulink software, MBD, SAM, NREL, LabVIEW, GitHub, TC1D, ORCAD, LTSpice, Visio, LaTeX. Before joining Nexteer Automotive, Dr. Brahmendra gained research expertise by successful completion of a DST project entitled Design of Renewable Energy-Based Hybrid Microgrid with Hybrid Energy Storage Systems, and backed by industrial experience as site engineer at Abacus Infrastructures, as well as input. Along with that one, he has worked as a research intern at BHEL R&D Division, Hyderabad, as well as an engineer trainee experience gained at Jahnavi Electricals, which is interconnected to APDCL substation. I'm glad to invite him. Okay, Dr. Brahmendra Kumar, we can start.
So thank you, Brahmendra Kumar. You are the youngest doctor of this FDP. And we are very much proud that you are an alumni of JNTUK. You can lead the session, Dr. Brahmendra.
Yeah, thank you. Thank you for the invitation, and good afternoon, everyone. Myself, Brahmendra Kumar.
I will stop the sharing. You can share your screen, please.
Yeah. So are you able to see my screen?
We are able to see Dr. Brahmendra. You can.
Hello.
Your voice is audible and your PPT is legible. Okay. I think you can keep it in the presentation mode. Was it already presentation mode?
Yeah.
Okay. Proceed, please.
Yeah, like myself, Brahmendra Kumar. Currently, I'm working as a systems engineer in Nexteer Automotive. So here I work for mostly electrical power steering systems. There I work for battery management systems and motor control systems. So today we are going to discuss about the microgrid systems, how it is going to impact nowadays along with the renewables. So current topic which we are going to discuss about the energy management of renewable energy based microgrid with hybrid energy storage system. So basically, the development and the application of renewable energy has experienced rapid growth over the last few years. So microgrid is a now major impact. So in that, we are including different sources, loads, along with the different kind of storage systems, all this together to form a microgrid. So what are all the things we can do based on this microgrid and based on for DC and AC microgrid and hybrid microgrids. So now we can start with the outline literature survey. Some of the researches which have already been done that we are going to discuss some of the researchers and some major problem statements that will occur from when you install some plans and all. From that we can design a microgrid system and some of the objectives along with some results and modeling and controlling part and stability analysis. Some references which have been used for all these works. So this is the basic introduction. So the renewable energy has experienced rapid growth over the several few years. So renewable energy, we all know, including solar, wind, fuel cell, hydro, tidal, and geothermal. So which are freely available and reliable also. So we are make it use of it how much efficiently. So when you started using these renewable energy sources to connect with the grid level, either DC or AC, how it is going to impact, what are the challenges. So first, in this work, majorly we have considered for solar systems, so that we can discuss in detailed way. When you install a solar plant, what are the challenges we will face, so how to overcome all those things. And this is the future area for along with the research plants and along with the microgrid systems. So microgrids are commonly designed for like all the different sources connected to their from a microgrid. So distributed energy sources, storage devices, and loads. So the microgrids are different. Microgrids means DC, AC, and hybrid microgrid. Hybrid microgrid is a combination of AC and DC. So some of the research sources they have considered for renewable sources along with the microgrid. So the first one they have used it for renewable solar along with the solar system, battery, and supercapacitor, and they have used it for the DC microgrid system. And second one is also they have used it for the DC microgrid system along with the AC. So in that they have integrated with the converter and inverter. So what are, when you want to exchange the power between the DC side and AC side, what are all the challenges? When it comes to AC, there are many other challenges have begun. So ancillary services, those things they have focused here. And the third and fourth, they have discussed when you install a plant, when clouds are moving over the plant, what are the challenges. So they have discussed about the few challenges related to when you install a solar plant. 3, 4, 5, 6, they have discussed about the those systems. And 7 and 8 they have discussed only about the when you integrate with the AC microgrid, what are all the ancillary services and what are all the current level and grid level, voltage level harmonics which are going to face when it is balanced and unbalanced conditions. Those they have discussed in 7, 8, and 9, 10. So we also have covered multiple things. Some of the major things which are covered when we install a plant, we have proposed a lot of techniques to overcome those challenges when it is applicable to DC, AC, and focused on the power quality also. All these four major things we have included in this presentation. So now majorly we'll talk about the problem statement. This is the we have considered one of the plants which is there in the BHL. So there we have recorded data for 1 year. So in when it is normal clouds, you cannot see the much radiation variance. There you can get the proper PV power. So at the time of level, we will not mostly we will not face any issue, because when you install a plant, most of the times when it is a fast movement of clouds because of air and all, the clouds will pass over the installation plant. At the time we will face a lot of issues. So when it is normal case, normal irradiation level will not face any situations. When it is fast movement of clouds passed over the plant, at that time this is the irradiation level profile. At the time we can see the major drawback of the power. So here we need to consider all the dynamics, and based on the dynamics, how we are going to maintain the continuous power to generate to the required loads and all, whether it is a kind of AC load or DC load. For that, we need to maintain the. Suppose when you are in the home, when you install some plant at top level, when clouds are moving, there we can see the lot of variations in the power level. At that time, we cannot maintain the continuous power. So what we are going to do that to maintain the continuous power. So for that, we have proposed a lot of controls. So some of the controls now we can discuss. So how these controls can integrate with the DC, AC, and power quality level. Those we will discuss further. So first we need to know about the control strategies. What are all the control strategies involved, and in which what is the best control technique to maintain those power fluctuations when you install a solar plant, either it is 500 kilowatt, 200 kilowatt, 1 megawatt. So first we need to analyze the controls, and after that we have considered some of the converters, like different converters are there: boost converter, buck converter, and another kind of interleaved boost converter. So we have taken here interleaved boost converter for the DC microgrid system. And after that we have extended our work to grid level, like AC. Once after the DC microgrid, when you connect with the AC microgrid along with the loads, what are all the challenges when you will face? Because sometimes the generating source may be greater than the load. Sometimes the generating source may be less than the required load. Sometimes mostly both can be balanced. So at that level, what we are going to, how we are going to maintain the continuous power to entire maintain the stability system. And fourth topic, we have discussed how we are going to maintain the sizing of the battery storage system. Suppose when you have taken 500 kilowatt of system or 250 kilowatt solar system, mostly when you based on the calculation, all most of the times we will use high capacity of battery. So when you propose some control for that, for the dynamics also, when you consider from the plant how it is going to vary, according to that, if you design any kind of battery, so we will reduce the capacity of the battery system. So all these four topics now we will discuss, and this is the objective one. So here our aim is to I think we have compared several controls. In that top two level controls only we have considered here ramp rate and step rate controls. So what are all the challenges when you taken ramp rate control, step rate controller, how it is going to maintain the stable continuous power? Those things we have considered here. And here we have used polarity systems to initial level. Most of the works we have considered polarity system, how what are the parameters required for to design a hardware level. Next step is hardware level, but initial level we have considered polarity system to confirm the what are all the parameters which you have chosen, which is used for the hardware level. So all these things which you have mentioned in this. So some comparison studies now we will see step rate control, ramp rate, low pass filter, moving average, and double moving average. So all these things we have mentioned. What is the storage time effectiveness and losses when you use that control, and degradation of the cycle. So in that, out of five, we have chosen to compare with the results step rate and ramp rate control. Finally, we are going to conclude that ramp rate control is the best control method to maintain the continuous power from the solar plant. So now we can see how we have compared those two controls. Generally, if you this is the basic when you consider solar plant, this is irradiation level. This is the lowest irradiation level. So this irradiation profile, when you see the this is the main, we are going to maintain this power. So this is the ramp rate control and this is the step rate control. So when movement of passing cloud happens, the power reduction will happen 100% to based on the fast movement of clouds, it will happen to at least some 10% of power. Worst case only it will go to zero, but we have considered almost 90% of variance happens. This control, these two controls will be used for to maintain the stability power. So when 90% power reduction happens, also at that time we are able to provide to maintain that we are map that power based on the storage systems. Those storage system we have considered battery and supercapacitor. So this is the block diagram and this is the power flow diagram. This is a PV system. One smoothing control is required. As we mentioned, interleaved boost converter, some converter is required. So we have converted that power to the higher level, and to bidirectional convert the two batteries along with the supercapacitor and DC load. Most of the works we have seen that one of the battery they can use in supercapacitor. So here we have used two batteries. The two batteries are controlled by only one supercapacitor. Those control we have implemented here, and this is the power flow diagram. So these are the basic equations. So input side and output side and DC load side. So input side we have already PV power, and the battery can charge and discharge, and supercapacitor also can charge and discharge. So all the time we have taken average of currents only. So higher level or lower level of currents when it is required 10 amps and it requires 4 amps. So we will always try to maintain the 5 amps average of that to maintain that continuous power. So, and also we have considered here how state of charge is like we need to maintain the state of health and state of charge levels. We have here state of charge also we have maintained that we have considered for the count cooling method. And this is the small signal modeling for our hybrid energy storage system. So this is the battery control loop, and this is the supercapacitor control loop. So we are maintaining to control the DC link level only. So here only we are going to control the entire DC links. We are going to map with the balance between the entire source side and the DC load side. For that only we have mapped this small signal modeling of HES. So this is the DC link. From that only we have compared. From that only we have taken the net current. From that only we have taken the average of currents that will pass to the batteries, and removal of this average current to net current is will go to the supercapacitor. As we all know, battery can support the maintain the continuous power, but whenever sudden changes happen in the battery currents, at the time battery system will not work, and battery system will go easily discharge and it will impact. At the time supercapacitor we are using to remove those transients and to maintain the stability power to support the solar system. So all these things which we have used, how gain calculation is happening, that we have explained here based on the formulas. How PA gains are calculated based on the which equations. So now we have plotted also Bode plot for current loop control and Bode plot for current loop control for supercapacitor. And this is the popularity system. If any of the industries and any of the organizations, if they want to test with the initial results based on the parameters, popularity system is the best system. So there we can fix that. I think here we have used a 40 kilohertz frequency related to popularity system. So always we try to use the 10 kilohertz to 25 kilohertz depending upon the system. So according to that, we are always trying to use the consider the parameters to make it work a proper system. Initially, we will do the software synchronization. Once we pass the software synchronization, after only we can attach to the program control board, and there we are going to do the hardware synchronize to get those results in the DSO. So this is the control board and all, and this is the operating system, and this is the operating software. There we can dump our model to the operating software. There we can connect all the ports. From that, initially we can pass the software synchronization. If any issue we faces, so we can get the code. From that code, we can debug the again our MATLAB model, and again we will connect with the after that we can do the hardware synchronization, get those results. So some of the parameters we have considered for this work: solar PV input system, some 40 volts, some converter parameters, battery capacity we have considered some converter parameters, supercapacitor related things, and so DC link voltage we are going to maintain at the 80 volts. Now so we can compare with the results both of the ramp rate control and step rate control. And when sudden changes happen, which control is providing more power along with the stability power. And also here we are going to check that whenever sudden changes in the load, we are able to maintain the DC link volt constant DC link voltage also. They are mostly in between plus 2 to 3 or max 4 we can accept, but when it is crossed more than that voltage level, so it is not a good practice to maintain that control. So here this is the initial level. So this is the solar PV varying depending upon the conditions. So this is the battery response. So battery is required to support whenever is some PV power is required from the battery. At the time battery will support. Whenever power is decreasing, at the time battery will support. Whenever the power is taken from the solar, that will store in the battery. So the supercapacitor is used to, so whenever sudden changes happens, those sudden changes will remove by the supercapacitor used to remove those transients. These are the two battery results, and this is the supercapacitor system results. So here we have varied randomly varying load profile. So any kind of variations happens at the load level. So here we have increased the max level. So we are going to see that voltage levels here, how it is varying based on our controller. So whenever you have varied load sudden changes happens, mostly we need to maintain the DC link voltage constant. This is related to step rate controls. So this is the step rate control profile for that battery. Two batteries are supporting that, and supercapacitor also. So here also we have considered the same load profile also. but how it is impacting at the DC link voltage. So here we are able to see the more voltage DC link voltage disturbances compared to the ramp rate control. So based on that discussion, so here we have analyzed. So this is for first diagram is for ramp rate control and step rate control. Here we are able to see the more voltage variations compared to the ramp rate control system. So this is the smoothing control, ramp rate control, step rate control, and we have analyzed here power level diagram also. So which control is produce more power along with to maintain the DC link voltage constant and also maintain the stability power. So here PV power with step rate control and PV power with ramp rate controls. So ramp rate control when you use it will produce more power compared to the step rate control. So and also we have used DC bus voltage like what level how much it is going to. So here we have consider peak overshoot system also, that is peak overshoot systems also. So when you use low pass filter control, when you use moving average, double moving average, step rate and ramp rate control, so that peak overshoot is also we have considered. So and also settling time also we have considered. So which control is going to settle fast when you use that control. So all those things we have considered here. And peak overshoot is the change in voltage by DC link voltage into hundreds. So that percentage also we have considered here. So all these things above findings so that ramp rate control provides faster regulation than the step rate control strategy. So so final outcome that we concluded that ramp rate control is the best choice to use for to disaggregate the further work. So initially we have finalized ramp rate control. So it is observed that it is more efficient in terms of efficiency, drop, losses, and the state of charge levels and cycling degradation and voltage regulation at the DC link. So here we have analyzed at what different time constant we have considered and what is the change of voltage and what is the efficiency of that variation of the voltage. So for step rate and ramp rate we have considered. Final outcome is that when you use these two controls for DC magnet system, so ramp rate control is the best storage efficiency, losses level, drop level, and system level also, and all these things and the voltage regulation also. This is the best control technique. So which we have used for this. This is a final summary. So efficiency when you use ramp rate control is 98, and when you use step rate control is 95. Remaining other controllers are very less compared to these two controls. So this is the one objective when you use the when you want to control the plant level variations. So ramp rate control we have finalized, and now we are going to take the some of the converters. Already we have multiple converters. So here we have used interlude boost converter for the same system. It is like a boost converter and interlude boost converter. How it will produce the like when you want to increase the voltage level when you give some 40 to 80 at the DC link voltage level, and how it is going to impact at the DC bus voltage also. So those converters we have uh, used here, and the ramp rate control we have already finalized it here. So this is the DC microgrid system. So solar, again two batteries along with the battery converters and supercapacitor. Here instead of boost converter we have used interlude boost converter along with the DC load. So this is the control structure. PV system is there. You are using ramp rate control. From that you are getting the battery currents. So that power management algorithm you are using and batteries SOCs, and two batteries SOCs you are implementing the power management algorithm, and DC link control. From that you are getting the net current. Removal of that net current from the averages you will get the battery supercapacitor current. So all those things we are using to pulse width modulation techniques to control that converter switches. So this is the control algorithm for the battery. When it is greater, there are two such sources. When it is produced more than the load and less than the load, at the time it can be the charging mode and discharging mode. So those modes, like you are able to produce the charge from the battery along with to maintain the load also. So that algorithm we have been implemented in this PMA, and this is the equations related to interleaved boost converter compared to normal converter. So all these things, what level of duty cycle, less than that, more than that, based on the input voltage. Suppose if you use 40 volts, like if you want to maintain that 80 volts, you used to use 0.5 the duty cycle. Again, we have used a popularity system to confirm that how it is going to impact and how it is going to get the results from when you use different converters, and different parameters we have considered here for the same different batteries, solar and DC load and DC link parameters. And the simulation results, when you are using boost converter, there we have observed DC link voltage is having high voltage ripples, and also current ripples also very high when you use boost converter. So for that we have used the interleaved boost converter to reduce this high voltage ripples and the current ripples from the like battery and supercapacitor systems. So these are the some of the simulation results. These are the results from the popularity. We have varied the. So this is the PV profile which we have randomly varied PV profile and load profile. So for that, how batteries are responding and how supercapacitors are responding, how we are going to maintain the stable DC link voltage. So this is the SOC profile for the both the batteries. So after all that, we have concluded that so interleaved boost converter is giving like best outcome. So it will regulate and it will remove the ripples also from the battery. So when you use interleaved boost converter, so when you want to maintain the steady DC link voltage during variable conditions, so it will increase the system reliability and reduces the ripples and convection losses in the system. This is the second outcome. And now already we have finalized RAM rate control. Now we are going to use that control for energy management system with the AC microgrid system. So it is a common of DC link along with the AC microgrid system. So here we have proposed key advantages. So efficient power sharing between the energy storage devices along with the fast regulation of DC link voltage in between generation and load variations, and effective power distribution between battery grid based on the different charge stages, and reduced charging and discharge from the battery current during steady and transient state fluctuations. So this is the renewable grid integrated with microgrid with hybrid energy storage system. This is the interleaved converter with the solar. This is the battery converter, supercapacitor converter, and DC load. And this is a microgrid converter along with the DC link. And here we have considered non-linear loads also. And this is the grid level. These are the filters. So all those things we have included. So how when you design a control, we need to control. We need to maintain all those things balances between the generation load, grid level, and everything. So here we have considered different modes: excess power mode and diffuse power mode and balanced mode. So all these things we will see further. So this is the control algorithm for that. So already we have concluded that ramp rate control is there, DC-link controller is there, grid current, battery current, and supercapacitor and battery currents. So all those things are feeding, and these things are going to control the converter and inverters. So this is the algorithm. This is the basic DC link voltage controller. So this is the DC link controller. From that we will get the error that will pass to the PA. There we have to design the PA gains. From that we will get the current that will pass to low pass filter. So average current we will get for the battery, and removal of that low pass filter current from the this DC current is the transient current. And this is the simplified control algorithm. So we have renewable sources, AC, DC load, and battery supercapacitor SOCs and battery supercapacitor currents. So microgrid operation we have considered renewable sources greater than the load, less than the load, and equal to the load. So how it is going to impact, and what are the challenges we are going to face, how we are going to maintain the system in any kind of situation. So lower level and higher level, and also we need to maintain the a state of charges in between higher level and lower level. So if you decide the system so 90 percentage, so you need to maintain, you need to charge the system at the 90 percentage level, and it should not, if you decided already 20 percentage, it should not go to below the 20 percentage of discharge state. So all those things also hybrid and source system operation we have considered here. This is the power balance equation for entire system. A designed renewable grid oriented microgrid hybrid energy system. Solar power. The HSS is the hybrid energy, means battery and supercapacitor. This can be charging and discharge. Grid power also we can take it and we get it back. And DC loads and AC loads. So this is the overall proposed control algorithm. So battery currents, and for that also we have used count cooling method to maintain that SOCs. And this is a DC link control, just now we have discussed. And from there we are getting battery controllers, and also we have using PLL and to maintain the grid current control. And also from previous system we are getting so ramp rate control. From that we are controlling the batteries and supercapacitors. And supercapacitor also state of charge also we have considered. This is the power flow diagram. We are getting the power from the different sources, how we are going to maintain the stable. So all those things references we will get from the control based on the EMS. So there we have defined some of the code logics when it is SOC is greater than the certain levels. So how much current you need to produce, and when it SOC is less than the like some certain level, so how much you need to discharge. So all those things we have mentioned in the EMS. From that finally we will get the reference currents that we compare with the actuals, and those we will feed to the switching pulses to control the converters and inverters. So this is the deficit power mode and excess power mode, two tables we have defined here. That is based on the SOC levels. When SOC is less than the higher level of the battery, and SOC a super higher level on the. So what you are going to take, this minus means actuals that we can produce, plus means you have to discharge. So all these things your battery is requiring to discharge the battery, and supercapacitor also is required, and the grid is also is asking for the net currents. So when SOC is greater than the higher levels, there you need not to produce any current from the battery. So all those things we have defined in the different modes based on the conditions of the battery, supercapacitor at the lower level and higher levels. So all the combinations, when both are low, when one is high and low, one is low and high, and both are higher levels. So when it is deficit power mode and excess power mode, so all those things we have considered in different modes of operation in the system. So the parameters which you have considered for this battery pack capacities, and how many batteries we have used, and for that converters switches, like how much inductance and capacitance required to control that converter, and supercapacitor values also we have used for that control converter parameters we have considered here, and PV parameters and DC load and DC load, and grid level parameters and filters also we have used it here. Suppose this is the like simulation results. This is the DC link voltage. Suppose this is the given PV power profile. So here T3 to T4, the PV current produced from the T3 to T4 is lower than the load demand. So that system works as a deficit power mode. In between T4 and T5, that system is the PV is increased over the load demand. So this is the excess power mode. So at the time excess power mode usually mainly to charge from the ESS, and IP again now it is lower than the load demand in between T5 and T6 instance. So again it will run as a deficit power mode systems. So different systems when PV power is greater than the load, less than the load, and like how batteries impact battery charging and discharging conditions, and we are also maintaining supercapacitors, and at the overall level how DC link voltage is being controlled by when you have given different profiles in any of the cases to maintain this as a constant profile, not more than the in between plus or minus 5 volts. So this is the battery current profile. Whenever there is a power required from the battery, battery can produce. Whenever it's not required, then it will charge the battery. And supercapacitor profile is used to remove all those transients. And this is the DC load we have varied in between the 2 to 4 ramps. So under different states, we have already discussed all those states we have explained here. When associate the battery is greater
నేను ఎందుకు
than
స్క్రీన్
the
షాట్లు ఇస్తాను సార్ రేపు పొద్దున వాళ్ళు గ్రాఫ్
so when at this condition, suppose when it is under differential power mode, state 1 conditions, so both are lower than the capacitor. So deficit power load shared by the battery with the grid power to match the maintain that levels. Again, stage 2 also one is less than the other, one is greater than of that. Which whatever we have seen in the table, that all those things we have explained in a detailed manner here. So at the time, what level, like which conditions battery will charge, which condition grid will support, at what level supercapacitor will absorb battery transients, all those things we have mentioned in different states of operation. So grid current also we have given here, and this is the voltage microgrid converter results. And this is the various power results in between PV power, how battery is supporting, and how supercapacitor is removing those transients, and how grid power is there on the AC load and a different DC load and voltage source converter. So as of now, how a system is maintaining the different condition we have seen, and some of the portions already some of the portions here voltage microgrid converter we have varied like unlinear way. So we have not given any linear profile. We have maintained unbalanced load only. So non-linear portion of the AC load at that point of time we have increased it at the T9 level we have increased. So at the time voltage source converter delivers harmonic components so needed for the load.
क्लास में पढ़ेंगे
So at the time when you have seen that non-linear harmonic components, you need to eliminate those harmonic components and you need to maintain the unity power factor at the grid level. So this non-linear, when you have seen that non-linear loads, so those harmonics will impact that under the system. So we need to remove that.
జయరాజు గారు ప్లీజ్ మ్యూట్ యువర్ మైక్ సార్
Participant, please mute your microphone, please. All the participants are requested to mute your microphones and turn off your videos, please. Dr. Brahmendra, proceed. Participants, Jairaz. Okay, Dr. Brahmendra.
Thank you. So now we are going to discuss about the power quality. Here at that level we have increased the load and also we have given non-linear profile. At the time harmonic components will impact.
May I know Jairaz? Yes. Thank you. Proceed, Brahmendra.
Yeah. So this AC load changes will reflected in the microgrid converter current. So this scheme is provides to harmonic and react to load current components. Those we need to remove and we need to operate a system at the unity power factor level. So that control also we have used here because we need to consider not only the balanced and unbalanced system. Unbalanced system also we have considered and we need to maintain the unity power, like sine wave currents and at the grid level, and we also maintain the utility system at the unity power factor level. So same whatever we have discussed with different conditions, we have taken the results from the OPLAT system again. So this is the performance under excess power mode of operation. So battery, all the currents values only. Here we have used only mostly current controls only. Only at DC link only we have used DC control. From that we have taken the current controls. So our PV current, when you have given constant profile, and how battery supporting, and how supercapacitor is reacting whenever sudden changes happen. Supercapacitors need to maintain that, remove those transients and DC load profiles. And when you change the DC load and AC load, how DC link voltage is impacting. So all these points, whenever DC load changes, this is a change in voltage, and whenever AC load changes, this is change in. So all the time we are maintaining that stability DC link voltage, whatever the condition we have given. So this is the AC load profile. Or after certain time, we have discussed that we have increased it to, at the time of 9, we have increased the system to, like current level we have increased. So voltages converters and grid converters. So all those things we have maintained. We have to remove the non-linear harmonic components to maintain that utility system at the unity power factor level. And this is different powers. So DC power, PV power, and the different battery powers. So how AC and grid level powers, how it is impacting. And this is at constant AC load profile, and this is at when you vary that AC load profile, what is the condition. And this is the voltage source converter current results, and also this is the non-linear system. When you design proper converter, at the time we are able to see that unity power factor conditions. This is a system for under deficient power mode system. So which is PV power under the deficit power mode. At that time we need more power from the battery and supercapacitor support. Same, most of the cases we have level of conditions we have explained. And here again we have varied stand to check the how grid currents and microgrid converters are impacting. At that time we need to compensate with the nonlinear harmonic components. So these are the different power level profiles. And this is the performance under various operations modes. So here we have included excess, deficit, and all the modes of operations. So yeah, at every level, whenever power required from the battery can support. Whenever PV power produces more, at the time battery will charge it, and supercapacitor will remove all those transients. And DC link voltage is the response of DC link voltage. And this is the random profile we have given, and this is the AC load profile and grid current profiles, and non-linear all the non-linear harmonic components we have injected to eliminate those components. So this is the different power profiles. So when you involve non-linear non-linear components, you need to maintain the utility power factor, right? So all these different modes of operations. So still we are maintaining that grid current and voltage for grid, and at the unity power factor level. So this is the power balance. So various power modes. This is a combination of, so already we have seen the power balance equations. So power balancing is input and output side. So input is a combination of PV, HCSS, and grid powers. So these are all the variables. So and this is a combination of DC and AC load powers. So when you have designed proper control at any kind of conditions, you need to balance these two powers. So here we have achieved similar profiles. This is because of the DC link voltage, but this is fine with that. So but we have maintained here both the profiles are maintained, input side and output side are equal. And this is between the various power modes. So already we have discussed excess power mode. At that time, what is our power balance equation, how it is going to meet. So again we have met at the excess power mode level also. And the deficit power mode also, we have given different conditions based on the AC load and non-linear components we have injected. So at that level in deficit power mode also, we are maintaining the power balance in between the input side and output side. And now we have like when you have designed, you need to focus on the THD also, so that the THD for load and grid currents we have considered here. Generally, when it is when you have used injected non-linear load, at that time we are able to see the 13.38 percentage of current run with non-linear load. So that while that current run by the grid is sinusoidal at the unit power factor level, so 2.4, this is within the general basic thing, 5% within that IEEE standards. We are maintaining the standards between the below the 5%. So we have achieved 2.14. This is profile with the when you have given a non-linear profiles, and when you have compensated with the harmonic component, this is the profile which you have achieved. And here also we have consider how like DC link voltage is peak or should how it is going to impact measured between the performance and rise time also we have included here. So the change in voltage we have added here based on the DC link voltage, and the time also, how much time is it going to settle also we have concluded, because whenever sudden load change happens at that time, we will not take much time to settle the DC link voltage. Even if we balance the power between generation and the load, but we need to maintain that DC link voltage constant, and it will come back to the very short period of time. So that profile also we have considered here. So those results also we have attached here. So here we have taken different references how they have considered, and this is our control along with the ramp rate control. So peak overshoot we have achieved 3.1, and settling time is very fast. This is in between 0.23 seconds. I think this is 0.23 seconds we are achieving. And grid current THD also we have achieved 2.14 percentage. So these are all the outcomes. So basic thing for this entire microgrid system, ramp rate control smoothens the PO power fluctuations, and it improves the reliability of the system. And also the control strategy which we have discussed now is capable of achieving compensation of currents and voltage also. And we have here single stage VSC, and if you want to use further three phase also, we can connect with the same system, and we can use it. And there we can see the more challenges. And we can use sinusoidal and space vector models also. Then from that also we can see the different outcomes and limitations how it is going to impact. And another feature of this system is the hybrid energy storage system also, which is supporting the entire microgrid system. So all these things are achieving and operating between the limits of the SOC regulations of the ESS. So under all the popularity and simulation results all are confirmed that it increases the power quality at the varied any of the conditions when you vary and responding to according to the conditions between the generation and the load. So the proposed control allows the renewable sources and the battery and the grid. All these interfaces are effectively meet the steady state or dynamics demands of the converter, because we have discussed about the different modes of operations. So all those things are achieved by this system. So the participation of hybrid energy storage system to handle the changes in the load and source side power, that is renewable power, and also achieve fast regulation of DC link voltage with the system. Now, in this force system, here we have taken entire plant profile. From that plant profile, how we are going to achieve how we are going to design the battery storage system, and also any fault happens when you have injected the three-phase system. Also, we have same control we have been used for the three-phase systems. Also, at the time any fault happens, like how we are going to control that fault. Here we have used LVRT control technique. So the system is mostly we have used for the sizing of the battery and the that fault conditions how we are going to support. So this is the system we have used with the three-phase system. This is the renewables and hybrid energy source along with the converters, DC link voltage. This is three-phase converter. These are all the filters. And this is the grid, and here we have used PWM techniques to control. These are the reference and actual currents, how it is going to control the entire inverter based on the SPPWM. So we have here PV and hybrid energy storage system, and phase lock loop, as we are all know aware of it, and the phase balance between voltage, phase balance voltage and frequency of the inverter need to match the grid, and synchronization of the grid is necessary. So those components, I think whenever any non-linear load happens, at the time we can see the harmonic components. Those can be reduced based on the LCL filter high frequency level components. This is the control diagram. So PV battery supercapacitor we are adding with that, and from that we are taking the grid ID and IQ currents. From that we are getting the VD. So then those VD VQ we have been used to control again the ABC by D alpha beta transformation techniques we have used, and again those after all that we are going to give the pulses to control the gate signals. So here we have introduced one new equation for that to control reactive power compensation based on the LVRT. This is the battery current basic general equations, the grid minus PV minus supercapacitor. So now, so this is for this profile, this set of equations or profile we can use for any of the plants. This is the one of the plant which you have considered here. This is the length and height of the plant. Whenever clouds moving over the plant at the time, we have already discussed 10 to 90% of the variation will happen. So at the time, based on the consideration of dynamics, we are going to produce the continuous power. So here we have measured the length also, length between the horizontal and vertical, those length and the capacity of the plant also we have considered to design the energy storage system. So horizontal dimension we have taken because when you the clouds, suppose when you think shorted period of time only we have taken, because at the time only we can see the dynamics of the variance of the power. Suppose if you ask the clouds are moving over the vertical, so at the time it will take long time to cover the entire plant. So for that only we have taken horizontal profile to within fraction of seconds we need to, based on the dynamics we can produce the power from the power from the energy storage system. So this is the irradiation profile of the year. Entire irradiation profile we have taken. So in that we have analyzed each and every irradiation of the each and every day average we have considered of the overall 365 days, and monthly daily average of the every each day, and monthly average also we have considered. And here we have average change of irradiation, monthly max and min, daily max and min. So all of those things we have considered, and we have discussed whenever sudden changes happen for that plant with that profile. Max in between the variations happens whenever fast movement of clouds happens. Basic daily change is between the 35 to 95, 75. For another plant, it may be between the 10 to 90 percentage. So we have observed that 35 percentage to 75 percentage. So the maximum speed of the cloud, which varies depending on the directional location, it is included by the PV plant. So the PV plant can be covered maximum cloud speed and can generate maximum power from the shortest amount of time and most extreme condition. That is about the dynamics of the system. So here is the tau we have correlated. So shortest dimension of the periphery at the PV plant. So shortest dimension also we have considered, and this is the wind speed also. So we need to consider the wind speed also. So that point also we have considered here. That is a constant parameter. This is the tau. So from that wind speed along with the dimension we can get the tau. And also here we have also excess and deficit mode also. Surplus means excess and deficit mode, deficit power mode, which is greater than 0, less than 0. How energy storage being calculated based on the power. So all those equations also we have included here. So this is the battery power maximum. So energy is a power into time. So we have considered here 90% of variations. Even if we have seen 75%, we have designed system for the 90% of variations. So this is the set of equations. So max ramp rate also we have considered here. So in this design, the capacity required to equalize the PV power variation control and capacity required for the most extreme fluctuations calculated. And sign of the fluctuations also we may unknown. So that's why we have taken dual battery capacity. So rising and falling of the fluctuations. Initial only we have seen that profile. So some period of time irradiation levels are high. Some period of time initial irradiation levels are very low. So we have considered capacity battery is the two cross into the energy of the battery. So rising and falling of the fluctuations. So all these things are being used by charging and discharging of the dynamics of the battery. So this is the transfer function from that controller, PA controller and PWM control system enter transfer function and open loop gains of the system, and how we have calculated those filter values and how we have calculated KPKA. Those equations also we have mentioned here. If somebody can utilize somebody is struggling to get calculation of those PI gains for three-phase system, these equations are sufficient to use to calculate the system, but we need to know the parameters of the, like how much source is required, how much outcome is required. Based on that we can calculate all those parameters. This is the border plot of the current control system, and we have considered here 500 kilowatt of seconds. So time constant is just 2 seconds of period of time we are going to achieve those dynamics. And already we have discussed shortest dynamics, shortest parameter of the P plant we have considered here. And grid voltage, DC link voltage we are maintaining 700 volts, and max value R max is 0.166. So battery power required is 462. So battery energy is 35. So 500 kilowatt of power we have concluded that 70 kilowatt of energy is required to maintain that power, and capacitor and remaining converter values also and filter values also we have mentioned here. And now we have achieved that how it is going to calculate. So now we are going to present with the grid current and the current results. Now it is in unity power factor level. So now it is in sinusoidal nature. So this is the PV power profile, how battery supporting supercapacitor, battery SOC, and how DC link voltage is regulating that. And these are all the grid voltage which are sinusoidal in nature, and this is the power from the P and Q. Now here reactive power is we have not considered any reactive power now. Now we will inject the sum of the faults. At that time we have used the LVRT technique to how to compensate the reactive power compensation. So at the time, so the active and reactive powers are shown already. In this case, the active power responded based on the control of the battery response to the grid, because there is no variation amplitude in the voltage. So reactive power is not shown. As a result, control is deactivated. IQ 0. So now we are going to activate this reactive power control. So now we have injected one of the fault at the grid level. So this is the grid drop we have given. At the time grid current also we have noted down. So this is the zoomed value of grid and grid voltage and grid currents. So grid voltage and grid currents we have given injected the fault at the time. General case, when there is no fault, reactive power is not activated, that control is also not activated. But when a fault injected, so reactive power, that equation control is activated to compensate the reactive power compensation, to maintain that again the same stability power. So now, so the power outages and voltage fluctuation generally cause the distribution system to quickly disconnect from the system, so increasing their use of power distribution system. So these units are required to assist the grid in the fault situation. So the signification of these requirements is a fault right through cable FRT, that equation we have used for FRT. So it basically allows the control design such renewable resource can remain associated with the system during abnormal conditions and contribute to voltage support the during and after abnormal operating conditions. So in that case, referent current generation, that equation method is used to propose a FRT control strategy to eliminate the oscillations in the active power in the unbalanced voltage dips and sustain the stable DC link voltage. So whatever we have discussed at a certain point of 6 to 7 levels only we have injected the fault. At that time it is regulated, maintain the constant grid voltage during transient fault. So control is activated immediately and reactive component power is compensated during between those time intervals. So this assists the grid in maintaining voltage stability even if of a fault. So reactive power is supplied assist with the voltage required based on the depth of the grid voltage sags. So in this fourth objective, we are concluding that So the solar power capacities requires only 70 kilowatt of energy batteries to smooth out the PV power variation due to relation temperature. So proposed power also regulate to generate reactive power compensation to assist the grid during a fault in maintaining the voltage stability also. And it is also associated with the voltage equation based on the depth of the grid voltage. So that equation will calculate till the depth of the, we have given a small level of voltage when it is given 450 to some 230 also, it will calculate the set of voltage to maintain that equation, and it will support the, it will generate the reactive power to assist the grid during the fault. So the proposed FRT capability is based on the referent converged generation method, and it eliminates the active power oscillation during unbalanced voltage dips. So entire power performance of the generator by the ramp rate control smoothly improves the grid stability and reduce the need of energy storage. So from that overall conclusions, initial stage we have described which control is being used further when you have used a solar plant. So we have concluded that ramp rate control, which is achieving higher efficiency. And the second and third object we have decided control also we have activated, and in that converters we have changed, and how it is like how it is being used for when you have used different converters to achieve the fast regulation of DC link voltage. And third objective we have integrated the AC grid. So when you have used it combined with the different sources, how it is regulating between the different modes of operations or regulation of DC link voltage, continuous stability power, and battery support and supercapacitor support and DC link voltage. All this level we have been used, and also it is increases the system efficiency. And fourth objective we have used how battery storage capacity when you have a plant, how much is required based on the some set of control algorithms. So this based on the dynamics, we can mention that suppose 500 kilowatt requires only 70 kilowatt of battery power to facilitate the power out from the PV variations. And also whenever there is any unbalanced load and load balance happens and reactive power and non-linear harmonics happens. So all those things we have been included in the different part of the work. So therefore it is a good way for future distribution system, the combined distribution power generation with the better power quality. Suppose somebody wants to use these kind of controls, and somebody wants to take reference from the our controllers and some like further controllers also. So future works involves in advanced control approaches and algorithms to improve power quality in grid integrated matrix system using hybrid and system. And PU power we have used ramped control, maybe like based on the advanced method and based on the advanced variants we can use different control techniques. And also we can use for large scale applications also this smoothing controls at the megawatt and gigawatt levels also to maintain stability power and improve system power quality. And hybrid like battery and supercapacitors also bidirectional converters are there. If somebody wants to take like advanced controls and all, they can use. And SOCs also we have used count cooling method. Somebody wants to use for Kalman filter method and all, and reference filters also they can use to control to maintain the state of charge of the storage devices. So different references we have considered for this entire work. And finally, I would like to express my gratitude to the organizer of the Atal FDP program and for providing me with this opportunity to present my work. I extended my heartfelt thanks to the fellow participants and my mentors for the valuable support. Thank you, everyone.
Thank you, Brahmendra. Dear faculty, it is our time to get clarifies any doubts. Brahmendra, what is your role in the next year automotive?
Senior systems engineer.
What kind of is there energy related?
Yeah, like here, electrical power series system is there. Where we are using battery powertrain level. We are using the
Faculty, please mute your microphone, please.
Brahmendra, I want to ask you one doubt.
Okay.
Now,
Proceed.
with the inclusion of energy storage technologies, that means again the complexity was going to increase because we are going. It is also an additional job to be tackled because these energy storage technologies will also vary. Therefore, if you are going to deal with different kinds of energy storage technologies, That means here also the intermittency comes into picture. Sometimes one energy storage technology was going to be offer more amount of storage. One was going to be at a lower end like that. That means there is a variations in energy storage also. Okay. Here we are using energy storage for the control method or control.
Yes.
Am I right?
Yes. To
Now,
support the solar level variations.
how can you compare the same? That means artificial intelligence can be used in this regard in future in your line of study. Am I right?
Yes,
Am I
sir.
right?
Maybe
We can use
further, yeah.
yeah. Now, in this case, that means how then in such a case, how can we compare this power generation control, power sharing control, ramp rate control, okay, from flexibility of this artificial intelligence?
But even though artificial intelligence only, it will give only some set of equations only, sir. But when it generates equations also, that again we need to incorporate into the models. From that only, again we are integrated with the hardware systems only, sir. Because artificial intelligence cannot solve at the hardware level issues, sir. Actually,
Fine.
artificial intelligence only we can it will give some set of support only, but it cannot solve the issues because on regular daily basis we cannot predict that different kind of conditions of the weather or environment. So those situations artificial intelligence cannot if we feed some data only, artificial intelligence can react according to that. But in the reality level only, we only need to work on it based
Yes.
on the different control algorithms, because in our lab setup we have extended with not only used only battery and supercapacitor, we have used fuel cell and
However, you have
lithium
used a super capacitor and you have very well, finally you have got very good result. Huh? I mean, it's really good. Fine.
and also we have used fuel cell also instead of using supercapacitor and battery. Our
For
fuel cell is only
continuous operation. Okay.
yeah, how fuel cell can eliminate the those dynamics and how
Okay.
it will going to support PO power. So we have experimented with the different storage devices. In
Okay.
this presentation, only I have mentioned some of the works. If
Yes.
somebody wants to further use, they can use fuel cell. They can incorporate into these controls algorithms. How it is going to impact, how it is going to work, and all they can check with that.
Okay. Thank you, Brahmendra.
Thank you, sir. Thank you.
Sir, any other questions? We can go ahead.
Yeah, any other participants, please. You can ask the any doubts, queries. So, in the light of your experience
Yes,
outside, do you suggest any modifications in the JNT because you have studied here? How far it is useful in the practical field? Any other modification do you suggest to us? Because we have renewable energy technologies as a PG course and thermal engineering offering special in renewable energy elective.
yes, sir.
What kind of
Actually, yeah. Actually, what we have done, sir, not only we have taken the grant from Department of Science and Technology. That grant we have used it for the one of the rooms, because suppose somebody wants to construct a house and some of the labs in the any of the colleges. So that experimented we have done in our lab. We have spent all the money to build a solar setup there. That power we have to take it from the solar power to use our room itself only. From that like we have developed all the system level and emulators and all we have used to get the power from the our lab, and that power whenever excess power is there we are going to give it to the another labs. Otherwise if your deficit comes we are going to use, so those kind of setups when you install in any of the colleges, then they can see the real time scenario of the how PV power is like responding to different conditions. All those things we have analyzed in our lab. How battery is responding, how supercapacitor responding, when somebody wants to use a different storage devices, how it is impacting. So all those entire setup we have involved. Mostly now I think world is focusing on the DC microgrid only. If somebody wants to take further any kind of PhD level research, I suggest that DC microgrid the best opportunity to work on the research level.
no, if would like to set up any experimental facility here, what would be the
Yes.
minimum cost as far as renewable energy is concerned, and what could be the objective while setting an instrument?
Basic level, I think 30 to 40 lakhs are sufficient for the emulator systems, sir. PV power emulator, battery emulator, and supercapacitor emulator, along with the O-polarity. Those those with equipments, we can feed a lot of data. At the time, we don't need the plant. Even if we have plant, those data we have taken, that data we can feed it to the emulator through the software. So we can analyze different kind of operations of the system. Then we can work on the okay, our PV power, like whatever the installed plant is not producing much power, then what we can do for that system. Because whenever we usually we will install the plants, because dust also will impact the system, solar system. So there are a lot of factors are involved, always being reduced the power from the PV plants. So we have done all these works, but only few only have presented. But in the JNTU level, I think I suggest that O-polarity system, all the time we need to do the hardwares. O-polarity system is the one of the equipment to decide the parameters, work on the
Brahmendra, we have purchased
hardware level.
O-polarity system. It is there in our electrical lab. Okay.
Okay,
That
sir.
too, you
Recently.
know that our entire campus is filled, on top floor is filled with the solar systems only, na?
Yes, sir. Yes, sir. Okay. So there we can use the parameters, because after once we have succeeded with the O-polarity, immediately we have purchased different components. There we have integrated on the system board, and there we have done the different set of experiments. So this is the like basic level practice. After that only we can go for the hardware level of things. So in our lab, not only for the getting the power from the solar lab, we have designed an entire charging station also to feed the like to charge the car. So EV car also we have maintained for all these cases, like whenever car charging is required, how much is required for the car charging, and powertrain level. So now currently I'm working in the next year powertrain level. So battery to motor EPS system, like how we are going to maintain that. Energy management between the battery to the EP system motor. So currently I'm working on all those controllers.
Okay. Any other faculty would like to ask Dr. Brahmender to clarify? So he has done nice work along with the calculations. He could done the equations, mathematical equations also he has shown. A good researcher. Any faculty
I
would
think
like to ask? Please.
every student in our JNTU, I think they can focus on the hands-on experience. Even the theoretical experience, if they have, they can always remember those things. But if they get the practical exposure, if they focus on the lot of experiments, they can see the lot of failures. Because we failed many times, we have damaged several equipments, and we have lost several thousands of money. But all these things based on we have gained a lot of knowledge based on the experiments when we have performed at the bench level. So
Okay.
I suggest that every student at least can perform by individual or group level. They can work on that. Then they can get the a lot of exposure that they will never ever forget.
Do we have any facility to offer internship to our students?
That I need to check with like my HR, sir. Once I will check with them if they offer any internship, then I can.
Okay. Thank
Because we
you.
have all the setups to
Yes.
different kind of experiment setups and vehicles also we have. Because here this is the EV electrical vehicle company, but even though we can see at the energy management level inside the system. So how it is performing, and then we have all the kind of motors, so how it is performing, how these controls are implemented. So here also we are using LabVIEW and all the hardware setups along
What
with the
is what
MATLAB.
capacity do you are using LabVIEW software?
Yes, sir, LabVIEW software.
At
Our
what capacity do you are using it?
which one, sir?
So for what type of analysis you are using LabVIEW?
No, sir, because we will integrate the our vehicle to the LabVIEW software, sir. There we can suppose vehicle is going on the road. Suppose customer wants to turn to steer the vehicle. So those all those performance we can do at the LabVIEW systems. So there's we can measure the torque and speed characteristics of the entire system. So system level, all the work we can do in the lab only. Then only we can understand the dynamics of the system, and according to that we can develop the new models, and after that we can build the software. The software we will integrate to the motor along with the ECU. That is called power pack. So I belong to power pack team. That power pack we will attach to the car, and then we can run the vehicle and see the results.
Okay, nice, Brahmendra. We have a
Yes.
nice lecture. Your contributions, research contribution, we are very much appreciated.
Thank you,
So
sir.
I thank personally on behalf of
Once again, thanking you, Brahmendra. Thank you.
yeah,
Thank you, sir. Thank you, Anish, sir. Thank you, sir.
accepting our
Thank you
invitation
both
and
of you.
delivering the lecture.